Welcome to this college algebra video on solving systems of equations using matrices. In the last section, we solved some systems of equations, mostly involving two variables and two equations, but we also solved some systems that had three variables and three equations. So what are some strategies we could use for solving a system that's that large? Well, can we use a graphical system? To the right, you see just a few of the ways that three variable systems could interact graphically. Each equation would actually be represented by a plane going through 3D space. And you can see that sometimes those planes are parallel, sometimes they intersect like a paddle wheel, sometimes they intersect two at a time, but not all three. Or you could have this situation where you have three planes that intersect at a single point. So that's just a few of the things we can have. But really, graphically, it's too hard to think about all the different possibilities unless you have a good 3D graphing program on a computer or something. It's pretty hard to solve a system of equations like that graphically. So what are our other choices? We could use substitution. It is possible, depending on the equations you're given. And as you saw in the previous video, if we have something called a triangular system, it's not too difficult, but not all systems are triangular systems. Can we use elimination? In the previous video, you saw me use a combination of substitution and elimination, both kind of interacting together to solve. And it is possible, but you have to really pay attention to detail. So the strategy I'm going to show you in this video is actually that same combination of substitution and elimination, just done with the help of something called matrices. So to understand what we're doing here, we need to first understand the concept of equivalent systems. So equivalent systems are systems of equations that have the same solution set. Let me give you an example. 3x plus 5y equals 35 and 2x plus 7y equals 27. That's a system of equations with two variables, two equations. It actually has a very simple solution. If you look at the tens place in CF3 and the units place in CF5 in this problem, and look at the tens place in CF2 and the ones place in CF7, that kind of clues you in here that x could equal 10 and y could equal 1. So 30 plus 5 would equal 35. 20 plus 7 would equal 27. So the solution of that system is 10, 1. Now it's not immediately obvious that that's the solution, but once you're told the solution, it's very easy to check. Let's look at another system of equations. X plus y equals 11, x minus y equals 9. This system of equations could also be solved with the pair 10, 1. It's a little easier to see. Here, 10 plus 1 is 11, 10 minus 1 is 9. So clearly this system of equations has solution 10, 1, and this system has solution 10, 1. That means that these two are equivalent systems. Let me give you another system. X plus y equals 11, y equals 1. That system also has the solution x equals 10, y equals 1. It is equivalent to this one, and it's also equivalent to the first. Now, which of these systems would be easiest to solve? Well, hopefully you would say that this third one would be easiest to solve because I can just do a substitution. Let y equal 1, put it up here, and you get x equal 10. This system here would not be too difficult to solve. If we do the elimination method, add the two equations together, we get 2x equals 20, and there we get x equals 10, y equals 1. This system would be a little bit harder to solve, but could be solved with elimination as long as you multiply the top equation by a number and the bottom of equation by a number. So we go from a hard system to a medium difficulty system to a pretty easy system. And let me give you one final system of equations. X equals 10, y equals 1. Well, that's a system of equations. It has two variables. There are two equations. And the solution is that x equals 10 and y equals 1. Now that is the easiest system of equations to solve. Our goal is going to be to take a difficult system of equations to solve and through a series of steps, turn it into a simple system of equations to be solved. The steps that we're going to be used are called row operations, and I demonstrated them in the last video. But this time, we're going to take a step before we do those row operations, and turn our system into something called a matrix. We're going to use the augmented matrix method of solving. And the first step in the augmented matrix process is to turn your system of equations into a matrix. So let me demonstrate how that is done. Let's say we start with this system of equations, 3 variables, 3 equations. We're going to take each equation and turn it into one row of a matrix. Now, a matrix is just an array of numbers. It's a rectangular table of numbers, essentially. That first equation is going to turn into the numbers -2, -5, 3, -6. So we've essentially stripped away the x, y, and z and written the equation as just a series of numbers. I could do the same for this second equation, since it's in the same order, x, y, and z, and then the number that doesn't have a variable. I'm going to rewrite this equation as the row 1, 3, -3, -12. And the final equation I'll turn into the row 3, -2, 5, 31. Now it's important that before you write the matrix version of this system, you have all 3 equations in a consistent format. So you need to have all the variables on one side and just a number on the other side. Keep the variables in the same order, x, y, z, x, y, z, x, y, z. Here's another example. We're going to turn a system of equations into an augmented matrix. Here's the system. Notice I have all the variables on the same side of the equal sign, all in the same order, x, y, z, x, y, z, x, y, z, and then the number that doesn't have a variable on the other side of the equal sign. We're going to turn each equation into one row of our matrix. So the matrix will have the row 1, -1, 2, 3 for the top, 2, 2, 1, and 3 for the next row, 1, 1, 3, and 4 for the last row. Now, sometimes you'll see an augmented matrix written this way with this up and down bar where the equal sign is on the original equations, so that the numbers that don't have variables are separated from the numbers that did have variables. On a calculator or computer, it's unlikely that you'll see this straight up and down line, but it's this last column of numbers that gives this method its name. That's the augmentation part of the augmented matrix. Now let's talk about transforming systems. There are certain rules that we can use in a process called Gaussian elimination. We are allowed to interchange the position of 2 rows. If you think back to the equations, it doesn't matter what order I write the equations in, they'll still have the same solution. Secondly, we're allowed to multiply any row by a non-zero constant. This would be the same as multiplying both sides of an equation by the same number. And we know that we're allowed to do that when solving equations. Lastly, you're allowed to add a non-zero multiple of one row to another. This is the process we learned about in section 5.1 when we talked about the elimination method, adding one equation plus another equation. And that again is a valid move when we're solving a system of equations. So what we're going to do now is do these kinds of operations with our matrix with a certain goal in mind. So here is a system of equations that I'm going to solve by the augmented matrix method. First, I need to write that system as an augmented matrix. The matrix would be 1, -1, 2, 3, 2, 2, 1, 3, 1, 1, 3, 4. I'm just reading the coefficients off the x, y's, and z's to form the rows of my matrix. So I'm going to take that original matrix and I'm going to add row 1 plus row 3. The reason I'm doing that is because I notice when I add row 1 plus row 3, I'll be able to eliminate a -1 and a +1 and get a 0. So this new row at the top is row 1 plus row 3. Notice that I left row 2 like it was, and I left row 3 like it was. When I'm doing this process, I usually like to only do one thing at a time. Next, I'm going to take row 2 and subtract 2 times row 3. What I notice is that 2 minus 2 will eliminate, 2 minus 2 will eliminate, so I get a 0 in the first and second positions of these rows. Now 1 minus 6 is -5, 3 minus 8 is also -5. Notice I left the top row the same and the second row the same. For the next step, I'm going to take row 2 minus row 1. 2 minus 2 gives me 0. 2 minus 0 gives me 2. 1 minus 5 gives me -4. 3 minus 7 gives me -4 again. My next step, I'm going to add row 1 plus row 3. And we get 2 plus 0 is 0. 0 plus 0 is 0. 5 minus 5 is 0. And 7 minus 5 is 2. So this new top row becomes 2, 0, 0, 2. For the next step, I'm going to multiply the top row by 1/2. Turns both of the 2's into 1's. 1, 0, 0, 1. I'm going to multiply the bottom row by -1/5. Makes the bottom row 0, 0, 1, and 1. And now this middle row, let's see what else I can do with that. I could add row 2 plus 4 times row 3. That'd be 0 plus 0, 2 plus 0, -4 plus 4, and -4 plus 4. Our result is 0, 2, 0, 0. And as a final step, I'm going to multiply that middle row times 1/2. Now I have 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 1. I'm going to take this matrix and turn it back into a system of equations. System of equations would be 1x plus 0y plus 0z equals 1, or 1x equals 1. 0x plus 1y plus 0z equals 0, or 1y equals 0. And 0x plus 0y plus 1z equals 1, or 1z equals 1. Each of these equations is very simple to solve. The first equation is equivalent to x equals 1. Second equation is y equals 0. Third equation is z equals 1. And I have my solution. Now, doing all these steps requires a good deal of practice. I knew that my goal was to wind up with a system of equations that had 1 in front of x, 1 in front of y, and 1 in front of z, and the rest zeros. What this is called is the row reduced echelon form of the original matrix. Row reduced echelon form looks like this. And when we have things in row reduced echelon form, they are very simple equations to solve. Now, what exactly is row reduced echelon form? Well, here's how it's defined. The first non-zero entry in any row is a 1. There are zeros above and below those ones, and rows are in order so that ones farther to the right are farther down the matrix. Essentially, what we're looking for is a stair-step pattern of 1s and 0s. If we can get our matrix so that the rows are in row reduced echelon form, what we will see is that the numbers in this final column are actually the values of x, y, and z. Now, doing this is actually pretty difficult, but fortunately, our technology is really good at doing this. It can do it very quickly, and it can do it for systems that are even larger than 3 by 3. Here's the calculator method for doing this augmented matrix process. First, convert the system to an augmented matrix. That's something you'll have to do on paper or in your head. Enter that matrix into your calculator. I'll show you how to do this on the examples, but in this directions, I'll kind of give you the buttons to press to start the process. So if you want to enter a matrix into your calculator, hit second matrix, edit, go across, And when you're all done putting your matrix in, hit second quit. Third, the calculator will do row reduced echelon form. There's a command to make the calculator go through that entire process. Change the matrix from the original form to the row reduced echelon form. The way you get to that command is hit second matrix, go over to RREF, this little symbol I'm going to use for enter, hit second matrix again, and tell it the name of the matrix that you're going to do the RREF of. Finally, convert back to a system of equations and you'll have your solutions. Next, I'll show you a few examples using a TI-84 calculator. Let's start with the system of equations that I just solved by hand. So the system was x minus y plus 2z equals 3, 2x plus 2y plus z equals 3, x plus y plus 3z equals 4. First job is to turn it into an augmented matrix. Well, we've already seen how to do that, and we know that the augmented matrix looks like that. Next is to put this matrix into my calculator. So I'll show you what I meant by those directions on the last page. I start by hitting second matrix. That's second, and I believe it's the fourth button down here, second matrix. And I'm going to go across to edit, and I'll put my matrix into matrix A. Right now, the size of that matrix is a 1-by-1 matrix. I need to make this a bigger table. This has 3 rows and 4 columns, so I'm going to say it's 3 by 4. And notice that now it has spaces to put all those numbers in. So I want to put all the numbers in: 1, -1, 2, 3. Every time you hit enter, it's going to jump to the next box. 2, 2, 1, 3, 1, 1, 3, 4. Hit enter one more time. And when I put in a matrix, I do like to double check, but entering a matrix into your calculator, just that simple. Second matrix, edit, then give it the correct size and fill in all the blanks. So looking this over, it looks like all of my numbers are entered in there accurately. So I'm going to hit second quit, second, and then the button right next to it is quit, and that gets us back to our main screen. Next, I need to tell the calculator to do the RREF process. So the calculator will do it, but I have to tell it to do it. Here's how I do that. Second matrix, go over to math, and I have to go a little ways down here. Keep going, it's quite a ways down. Choose RREF, don't stop on REF, go all the way to RREF for row reduced echelon form. Hit that, and the calculator is still waiting. What does it want to do RREF to? We got to do this one more time, second matrix. And notice my list of matrices now has A filled in with that 3-by-4 matrix. So hit enter. We want to do RREF to matrix A. And I'll hit enter, and just that quickly, it does all those steps to change that matrix into row reduced echelon form. So the calculator just determined that row reduced echelon form looks like this. That means converting it back to a system of equations: 1x equals 1, 1y equals 0, and 1z equals 1, and we get that solution we saw previously, 1, 0, 1. Now, I think you will agree with me that that is a good deal quicker than the way I solved it by hand previously. Now, there's nothing special about a 3-by-3 system. This augmented matrix calculator method can work for smaller systems as well. If we have a system of 2 equations and 2 unknowns, like you solved a lot of those in section 5.1, we can turn that system into a matrix. The augmented matrix will just have 2 rows this time. The first row will be 4, -1, -10. The second row will be 3, 8, -25. So I'm going to put that system into my calculator. Hit second matrix, go over to edit, and you can just edit over top of a previous matrix. So I usually just choose A again. And this time I want it to be 2 rows and 3 columns. So I make sure that's the correct size. It does look correct. Put in the numbers I want: 4, -1, -10, 3, 8, -25. Hit enter and go back and check my values. Everything seems accurate, so I hit second quit. Now I have to tell the calculator what to do. Say second matrix, go over to math, work your way down the list until you find RREF, and the calculator is wondering, RREF of what? Second matrix A. Do RREF to matrix A, and the calculator finds that it's 1, 0, -3, 0, 1, -2. Translate this back into a system of equations, and we'll get 1x equals -3 and 1y equals -2. Notice that the 1 here is in the x position, the 1 here is in the y position. So x equals -3, y equals -2. Solution of that system is -3, -2. And if the calculator can solve a smaller system, do you think maybe it can solve a bigger system? Well, let's try a 4-variable, 4-equation system. Again, the first step is to write this as an augmented matrix. So the first row is going to be 5, 2, 4, -10, 18. Now, as I look at this second equation, I notice it's shorter than the first equation. I see that it's missing a W term. So as I write the row for this equation, I'm going to need a 0 in the W column. So my row is 0, 8, 3, 4, -28. The next row seems correct. Everything's in the proper order, and it has all 4 variables. So this row will be 2, -6, 9, -7, 57. The last row is short also. Now, what variable is it missing? It's missing the y variable. So I'll have my first 2 columns, 10, -2, then a 0 in the y position, then 16, 84. So there's the augmented matrix for that system of equations. Put all this in the calculator, have it do RREF, and you're going to get this result: 5.68617. If a decimal version of these answers is not acceptable, it is sometimes possible for your calculator to turn all those decimals into fractions. All you have to do is hit Math Frac, and you'll be able to turn all those numbers into fractions. So this system of equations doesn't have a very pretty answer, but at least it has an answer. There is one single point in 4-dimensional space where all 4 of these equations will intersect. Now, in the past, when we've solved equations or solved systems of equations, we've seen that sometimes there can be no solution and sometimes there can be infinite solutions. So how would we recognize that when we're using a matrix method to solve our system? Well, for one solution, you're going to get exactly what we've just previously gotten. You'll get a bunch of rows in row-reduced echelon form with that stair-step pattern of ones and a series of numbers down the right-hand column. That is the one solution for that system of equations. To recognize no solution, what you're going to look for is a row that has all zeros and then a number in the last column, some number not equal to 0. If you see a row like that, that means that the original system of equations had no solution at all. And finally, infinite solutions. To recognize infinite solutions, look for one of the rows where all the entries are 0. All the way across, even the final number is a 0. If you start with a system of equations where there are fewer equations than the number of variables, that system is either going to have no solution or infinitely many solutions. If there are infinitely many solutions, we'll talk about how to write those infinitely many solutions in terms of one of the variables. Let's solve this system of 3 variables, but only 2 equations. And when the directions say use Gauss-Jordan method, that means that you can use the augmented matrix method as well. So our first job is to turn this system of equations into a matrix. It'll have 2 rows, first row being 2, -5, 3, 1, second row 1, -2, -2, 8. We'll have the calculator do the RREF process, and we get these 2 rows, 1, 0, -1638, 0, 1, -715. The solutions are not 38 and 15 because this top row does not represent x equals 38. It actually represents x minus 16z equals 38. And the second row actually represents y minus 7z equals 15. Now each of these equations can be solved so that one of the variables is by itself. In the first case, it's easy to solve so that x is by itself. X equals 16z plus 38. In the second case, it's easy to solve for y to get by itself. Y equals 7z plus 15. So when I write my solution, we're going to write a solution set, and we say that it's written with z arbitrary. So in place of x, I write the expression 16z plus 38. In place of y, I write the expression 7z plus 15. And in place of z, I just put the variable z. What this means is that I could pick any value for z, and I could generate a set of 3 numbers that would solve this system of equations. For instance, I could let z equal 0, and my triple would be 38, 15, 0. I could let z equal 1, and my solution would be 16 plus 38 for x, 7 plus 15 for y, and 1 for z. I could let z equal 2. I'd get 32 plus 38 for x, 14 plus 15 for y, and 2 for z. And I could do this with as many z values as I want. So there are infinitely many solutions, all having this relationship. If I start with any z value, I can come up with a triple of numbers. Now this is the way you'll need to write your solution if you do RREF and get one row that is all zeros. So that's going to do it for solving systems of equations using matrices. Go ahead and get a calculator out and try some of these yourself, and I'll see you next time.